If it's okay with you guys. Maybe we'll just finish out the terminal craps. Let me fire up the spreadsheet real quick. Oh, you can't see that. So here's what I've done up here in Excel. Let me roll that out so you can see it better. Now what Excel is going to do for us is it's going to be a perfectly random game. If you click in these cells, you'll see what's going on. This is going to keep track of how many games we play. That's what keeps track of how many games we play. Right here, it's kind of shaded out, but that little cell there says prize is behind. It is using the random integer command 1, 3, just like I was doing, to put the prize behind a door. Fair enough? So it's going to be random just like I was being. That part I was okay with, even though it pissed off Deb and I apologize. Okay? Then, your choice, here's where I think this does better than us. It's going to randomly pick a door 1 to 3, which means all those worries I had about you guys picking too many door 2s or too many door 3s, this is going to even it out, and we're going to pick randomly from those doors. Monty shows you, here, this is a fun one. Look at the command up there in that bar. This is what I had to do mathematically to correct for that problem Justine picked out. Now, you notice it's an if command? It's an if command. The if command means if you pick the correct door, which means if the door you picked matches the door the prize is behind, then I got issues. Then I've got to solve this goofy-ass equation, which was so much fun, by the way. But if they don't match, the choice is easy. Pick whatever's left. Does that make sense? So that's what this little command right here is. If you guys pick the door the prize isn't behind, which is going to happen how often? 2/3 of the time, right? That you're going to miss the door 2/3 of the time. I'm sorry, that was an unfair question, because you just told me 1/3. You pick the door, the prize is behind 1/3 of the time, which means you don't pick it 2/3 of the time. Is that fair? So if that happens 2/3 of the time, I simply respond to this. Otherwise, I go to that. And that has to be, I have to be random for that. And that's what that freaking function up there does. And then, as far as deciding how to switch, I make that random too. I make that random. It's randomly picking a 1 or a 0, depending on what the result of that cell is. Okay? And the result is, you win or you lose. You're going to see you win and you lose as this thing keeps track. It's going to keep track over here in this chart, and the percentages are going to show up down here. So every time I press F9, we get some results. Okay? Make sense? So right now, if I just stopped right now, it looks like we win 43% of the time if we switch, and we lose 57% of the time if we switch. If we stay, we win 40% of the time, and we lose 60% of the time. So right now, it looks like we suck. Because no matter what we do, we're losing a higher percentage of the time. But I've also only done 12 trials. Right? We did about, what, 100 or so? No, more than 100. 150? Let's go up to 150 and see if it looks anything like our results. Okay, there's ish. Look anything like our results. If we switch, the chance you win is 61, the chance you lose is 39. That's getting close to what we got, isn't it?
That is.
This is not close at all to what we got. This is saying if we stay, we're going to lose more than we win. Stable time? Stable time, yes. All right, here it goes. Are they starting to stabilize a little bit?
No.
Well, they're bouncing, but they're not bouncing as far. I guess that was, I'm sorry, the definition of stable is a little bit tricky there. We'll answer that question a lot better on Monday when I have you guys play with the dice, because I've got some simulations for dice too. The beauty of this is doing just what we did, but it's doing it better. Michael, go.
Is this on the website so we can play with it?
I can get it to the website. Send me an email, remind me to post it for you. You can have it. Yes, I'll give you all the simulations you want.
Sweet.
I've got about half a dozen for you guys that we're going to play with the next couple of days. They're all yours.
Probably change it on the bottom.
This one is staying pretty true to what Rob said it was. 67, 33. It's a little bit of fluctuation here and there, but Trey brought this up last week. You're going to have fluctuation. It's going out over infinity.
That's the same. 60-30, 60-30.
67, 32, 67, 33. So 2/3, 1/3, 1/3, 2/3. But look at where the 1/3, 2/3 is in the stay. It's now looking like we shouldn't stay. It's now looking like we shouldn't stay. It looks like we only win 1/3 of the time when we stay, but we win 2/3 of the time if we switch. Now hopefully, over the course of the next 5 minutes, because that's all we have, That's going to make they're identical. Now, I have not programmed Excel to make them show up identically. Not at all. I have not. Hi. I have not these. You guys hopefully are seeing these numbers are operating independently of each other. But it looks like this number matches that number, and that number matches that number. They have to. They have to. And here's why. I'm going to wrap this up if you don't mind. Here is an analysis of the results. Here's what happens if you pick and stay with a door. Okay? Remember what Aaron said? When you pick the first door, what's the chance you're right? 1 in 3. That means you picked the correct door 1 out of 3 times. If the lollipop is behind door number 1, and you pick door number 1, then you win. But if you pick door number 1, isn't it twice as likely the lollipop is somewhere else?
Yeah.
So 1/3 of the time, if you pick and stay with your door, you get your lollipop. But it's twice as likely the lollipop is somewhere else. And that works for all the doors, doesn't it?
Yeah.
That works for door number 2. If you pick door number 2 and stick with door number 2, and the prize is actually there, yay. But it's twice as likely the prize is somewhere else. Same thing with door number 3. So you see, of the sounds like your project. 3 outcomes for your door pick, 3 outcomes for the location of the prize. 3 times 3, 9. Yes? Of those 9 outcomes, only 3 of them, you pick the correct one. Compare that to what happens if you switch. This is what happens if you switch. This admits that what most likely happened when you picked your door?
Lost.
Most likely you picked the wrong door. So if you pick door number 1, the only way you're going to lose if you move is if the prize was actually there. But the prize probably isn't there. It's probably somewhere else. That's why. And I don't know how it got mixed up with our data as half and half. I'm guessing all those psychological things kicking in. I don't know. But we saw it show up almost perfectly with our switchers, didn't we? The few that switched, 2/3 of them won, and 1/3 of them lost, which is exactly what's supposed to happen. These are the 1/3 that lost. Here are the 2/3 that won. Isn't that rad now? If you've seen the movie 21, this problem makes a cameo in that movie. It's called the Monty Hall problem. What should you do if you're on Let's Make a Deal and Monty gives you the choice to switch or stay? You just learned that you should switch. Twice as likely to win if you switch. Not 100% likely. Not 100% likely, but twice as likely. Does that make sense? Some of you might not buy it, and that's okay. If anybody doesn't buy it, who doesn't buy it? Who doesn't buy it? It's okay if you don't buy it. You all buy it? Hot damn. Okay, you don't buy it. Trey, good. Good. No, that's good. I didn't buy it right away either. And this is why I ask. This had to make sense to me on a trail run through Brandywine Creek State Park back in Delaware, about 98. Running down a trail, Brandywine Creek State Park, and it hit me as I jumped over I can show you the tree if we're ever there together. I can show you the tree it happened. I jumped over it and I was like, son of a bitch. There it is. It clicked then. Here's how I came to peace with it. Here's how I came to peace with it. Imagine, instead of 3 doors, there are 10. Your job is to pick a door. Trey, you pick door number 5 randomly. What's the chance the prize is there? 1 in 10. 10%. Pretty crappy odds, yes? Monty now does this. So there's the door Trey picked. There's the one door he didn't open. Would you switch?
Yes.
To door number 9. Assuming there's one prize and he didn't move it. Would you switch?
Yes.
Trey's saying no. Everybody else is saying yes. I sure as hell would. Because what's the chance it's behind that door over there?
That's good. That's a good chance.
1 out of
90%. It's only 10% behind this door. 100% of the time it's behind one of these doors, yes? What's the chance it's behind this door? 0. This door? That 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 door? 10. I didn't move it, right? So what it has to be here? 90. You're 9 times as likely to win if you switch on this. A little more obvious. But the same thing applies here, right? You ready? You ready? Lollipop, close your eyes. Oh, no, not to do it. We're done anyway. Here, pick a door. Door number 2. I show you door number 1 is empty. Now, when she started, What was her chance of picking the right door? 1 in 3. This door also had a 1 in 3 chance when we started. And so did this one. But when I open that door, this is now 0. But that doesn't change this. You're still right only 1 in 3 times. The unknown over here, though, has to pick up the extra 1/3. It has to pick up the extra 1/3, which means Aaron, who got it, was only going to get it 1 in 3 times. The other 2 out of 3 times are going to be over here. Does that ish make sense? Chew that over in your mind. Let your mind kind of play with that. It took me a jump over a root of a tree. Exactly. It's definitely a fun problem. Definitely a fun problem. If you don't mind throwing the dice, I'll put the dice bin right here. We'll play with the dice next time. We'll show you how to use that to figure out craps, figure out Powerball, figure out Monty Hall.
So why wouldn't that,
Go ahead,
you
Drew.
said 90%, so why wouldn't that make it 50-50?
Because I didn't move the prize. When you picked that door originally, you were only 1 in 10.
How are you?
You're still only 1 in 10. Opening doors doesn't change the fact that you probably picked the wrong door in the beginning. Did you ever watch Deal or No Deal? That show with Howie Mandel? I've only watched it a couple times, too. It's nuts. Have you ever seen it where it gets down to 2 suitcases? Okay, at that point, is it 50-50? No, it's crappy, really good. Because the chance of you having the suitcase with all the money in it is basically 1 in 26, which is 4%, right? Same logic here. These are suitcases held by the little models in their dresses. Yes? This is the suitcase you have in front of you with Howie. These are all the suitcases that get opened for the banker, and that's the last suitcase waiting for you. You have a better chance it has the prize.
Yeah.
Does that make sense? Keep thinking about it. It's not the easiest thing to process. Although I think Cassie picked it up pretty quickly today.
Really cool. Yeah.
Isn't that badass?
Blows my mind.
It's kind of cool. I mean, I think it's thank you for the insights, Rob. I think it's totally rad. It's one of the neatest problems in mathematics, I think.